Okay, let me try and walk you through the gist of this homework problem. So we have the capacitors. Initially, nothing has a charge and connected with switch open. Right off the bat, if this switch is open, nothing flows through this. So we can redraw our circuit, just taking that switch out. Nothing flows there, so there's no need to have it in there. The applied potential difference is VAB equals 210 volts. What that means is we've basically hooked up a battery to A and B, got a positive end, a negative end. This battery has a potential of 210 volts. So A is at a high potential and B is at a low potential. If you wish, you can think of point A being at a potential of 210 volts and point B being at a potential of 0 volts. So you can think of it that way if you wish. All right, the next thing we'll do is let's recognize that the 3 and the 6, those are connected in series. So you can do a series equivalent. And you can find the equivalent capacitance doing 1 over 3 plus 1 over 6 to find that the equivalent capacitance is 2 microfarads. Okay, likewise down on the bottom, that's a series equivalent. And that equivalent capacitance is going to be 2 microfarads again. Now you can redraw your circuit. So we've got point A, we've got an equivalent on top, got an equivalent on bottom. So here's A, here's B. This is 2 microfarads. This is 2 microfarads. For those 2 microfarad equivalents, they're each going to have a potential of 210 volts because the potential between A and B is 210 volts. Which means you can find the charge. Charge is capacitance times potential. 2 times 10 to the minus 6 farads times 210 volts. So the charge is going to be 420 times 10 to the minus 6 coulombs, or 420 microcoulombs. All right, so that's what's happening with the equivalent. Now what we can do is we can back up a step. Since this equivalent has a charge of 420 microcoulombs, each of these has a charge of 420 microcoulombs. This is 420 microcoulombs. This is a series equivalent of these two, so those also have 420 microcoulombs. So let's back up. Let's write the charges there. Let's find the potentials there. And then we'll get into part A and see if we can find the potential difference between points D and C. We know the charge and the capacitance of each of our 4 capacitors. Let's use our equation that potential difference across a capacitor is equal to the charge on the capacitor divided by the capacitance. So let's apply this to each of our capacitors. So for our 3 microfarad capacitor, the charge is 420 microcoulombs. The capacitance is 3 microfarads. This gives a potential across this capacitor of 140 volts. For the 6 microfarad capacitor, the charge is 420 microcoulombs. The capacitance is 6 microfarads. Q divided by C gives us a potential of 70 volts. Likewise, down on the bottom, the 6 microfarad capacitor has the same charge. It has the same potential difference across the plates. And the 3 microfarad capacitor also has 140 volts across the plates. Trying to find the potential difference between points D and C, so we have to think as we go from A to B, does the potential increase or decrease? So A is at a high potential, so when we hit our top capacitor, to get to a low potential over here, there must be potential drops as we go from this capacitor to point B. So across this capacitor is a potential drop or a potential decrease. Likewise across this next capacitor, this is a potential drop. Then as we come back around the circuit to go from B back to A, the potential must increase. So we'll have a potential increase across this capacitor and an increase across this capacitor. Okay, so to go from high to low, we have to decrease. To go from low to high, we have to increase. All right, now we're looking at the potential difference between points D and C. To go from D to C, first you have to drop by 70 volts. So our delta V that we're asked to find equals a drop of 70 volts. So drop means negative. Why don't we even put that in as a note? So we have a drop. But then to get back to C, we have to do an increase of 140 volts. So we drop 70 here, we increase 140 here. So the potential difference as we go from D to C is equal to positive 70 volts. Overall, the potential is an increase of 70 volts. So there's the outline of how to do part A. Next, we'll look at part B. For part B now, we're going to close the switch, and after we close the switch, what's the potential across every capacitor? So if we close the switch, we make this a line. That means charge is now free to flow through this branch. Let's redraw it. So there's our 3 microfarad, there's our 6 microfarad, and we've got that line going down the middle. 3 microfarad, 6 microfarad, 6 microfarad, and 3 microfarad. If we want to find the potential across each, and we know that the potential from A to B is 210 volts, what we have to do is we have to draw an equivalent circuit. So let's look at the connections. So the 3 and the 6 here are connected top to top and bottom to bottom. Likewise for this 6 and 3. So these are in parallel. And these are in parallel. So our next step should be to find the equivalent capacitance between these two. When things are in parallel, you just add up the capacitance to get the equivalent. So the C equivalent here is 3 plus 6, 9 microfarads. Likewise, on the right-hand side, the C equivalent is 9 microfarads. So we'll draw a new branch. So point A, oops, I drew it a little bit funny. Okay, so we go point A, goes to an equivalent of 9 microfarads to an equivalent of 9 microfarads. There's A, there's B. Each of these is 9 microfarads. These two capacitors, these are in series, and we know how to find a series equivalent. 1 over C equivalent is equal to 1 over 9 plus 1 over 9. So the C equivalent here is going to be 4.5 microfarads. Okay, so let's draw one more equivalent. I think I can even squeeze it in down here. So now I've got point A, point B. The overall equivalent capacitance is 4.5 microfarads. And I know that the potential between points A and B is 210 volts. What I can do with this information is find the charge on this equivalent capacitor. Then I can start to work backwards, finding the charge and the potentials on all the other capacitors. Okay, so we know that charge Q is equal to C times V. So I've got 4.5 times 10 to the minus 6 farads times 210 volts gives me 945 times 10 to the minus 6 coulombs, or 945 microcoulombs. This is a series equivalent of these two. So these two are going to have the same charge, 945 microcoulombs. I'm going to draw that on the next slide. So we just found this result on the previous slide. Working backwards, the 4.5 microfarad was the series equivalent of the two 9 microfarads. Things in series have the same charge, so each of these 9 microfarad capacitors has a charge of 945 times 10 to the minus 6 coulombs. With the charge and the capacitance, we can find the potential. We remember that potential is charge divided by capacitance. So for each of these two capacitors, we'll do the charge, 945 times 10 to the minus 6 coulombs, divided by the capacitance, 9 times 10 to the minus 6 farads, and we can get the potential on each of these two capacitors. So that's going to be 105 volts on this one. So that's this one. And 105 volts on this one. All right, now we're going to back up another step now that we know the charge and the potential for each of these, remembering that each of these were parallel equivalents of what came before. For our final part of part B, we have to remember that each of these 9 microfarad capacitors were a parallel combination of a 3 microfarad and a 6 microfarad. We also have to remember that things in parallel have the same potential. So this one has a potential of 105 volts. That means this one is 105 volts, and this one is 105 volts. Likewise, this is the parallel combination of this 6 and this 3. Things in parallel have the same potential, so these also have a potential of 105 volts. Okay, and that's what part B asked for, was what was the potential difference across each of them after the switch is closed. In part C, we're asked how much charge flowed through the switch when it was closed. So let's look at what's going on for this little stretch of the wire. Let's see what's the net charge right here when the switch is open. And let's see what's the net charge right here when the switch is closed. Whatever that difference is, that's how much charge flowed through. Hopefully that makes sense. Okay, so when our switch was open, we know that our 3 microfarad capacitor carried a charge of 420 microcoulombs, and our 6 microfarad capacitor carried the same amount of charge because those two were in series. What that means is that our plates were plus and minus, plus and minus. We're looking for what is the charge along this stretch right here. So the net charge right here is minus 420 microcoulombs plus 420 microcoulombs. The net charge in the beginning equals 0. So that's the net charge in the beginning. What about the net charge at the end? We didn't calculate the charge on each of these capacitors, but we could do that now. We know that the 3 microfarad capacitor carried a potential of 105 volts. We could do charge equals potential times capacitance to see that the charge on those capacitor plates is then 315 microcoulombs. This plate is positive, this plate is negative, so this plate carries a charge of minus 315 microcoulombs. Okay, what about our 6 microfarad capacitor? That also had a potential of 105 volts. If we do Q equals V times C, we get a charge of 630 microcoulombs. This plate is positive, this plate is negative. This plate carries a charge of plus 630 microcoulombs. If we're looking at the net charge in that stretch, it's going to be minus 315. So Q net equals minus 315 microcoulombs plus 630 microcoulombs to give us positive 315 microcoulombs. So in the beginning, there was no net charge on this stretch. After we closed the switch, the net charge for this bit was 315. So the amount of charge that flowed when we closed the switch was 315 microcoulombs.